Ladies and gentlemen, welcome back to the channel where we analyze the future before it actually decides to show up and ruin our current comfort. Today, we are talking about something so small that if you sneezed while looking at it, you'd effectively be committing a mass robotic genocide. We're talking about robots the size of a grain of salt. And no, I'm not being hyperbolic for the sake of the algorithm. These things are literally smaller than the coarse salt you put on your avocado toast to feel sophisticated. A team of absolute mad scientists from the University of Pennsylvania and the University of Michigan just dropped a bombshell in the world of nanotechnology. They've created what they're calling the smallest fully programmable autonomous robots ever built. We are talking about machines that can swim, sense their environment, and make decisions without a human holding a remote control. It's like Honey, I Shrunk the Kids, but instead of a weird Rick Moranis invention, it's a terrifyingly efficient feat of microengineering. Let's talk dimensions, because size matters, especially when you're trying to navigate the bloodstream without causing a massive biological traffic jam. These little guys measure roughly 200 by 300 by 50 micrometers. To put that in perspective for those of you who aren't currently holding a microscope, they are about 10,000 times smaller than any autonomous robot we've seen before. If a standard Roomba is a blue whale, these things are, well, they're basically plankton. But plankton with a PhD. And here's the kicker: the price. Usually when we talk about cutting-edge robotics, we're talking about millions of dollars in a government grant that could fund a small country. These robots? They're projected to cost about 1 cent per unit. A penny, you could buy a fleet of 10,000 microscopic robots for the price of a fancy latte at Starbucks. Imagine that. You drop a penny on the sidewalk, and instead of just losing a useless piece of copper-plated zinc, you've just abandoned a high-tech autonomous explorer. But how do you build a robot that small? You can't exactly go to the hardware store and buy tiny little gears in WD-40. The architecture here is a masterclass in integration. The University of Pennsylvania handled the body, the active structures at the microscale, while the University of Michigan provided the brain, a microcomputer that is a miracle of low-power electronics. At the heart of this speck of dust is a microcomputer about 100 micrometers wide. It's got a processor and programmable memory. Now, don't expect it to run Crysis or even a decent game of Snake, but it has enough juice to store basic commands and control logic. It can feel its surroundings, process that data, and act. It's a complete system integrated into a footprint that makes a dust mite look like a landlord. Now, let's talk about the power problem. If you've ever been frustrated that your smartphone dies after 6 hours of scrolling through memes, imagine trying to power a computer the size of a human hair. You can't exactly plug it into a wall box. The team at Michigan had to reinvent the wheel, or rather the circuit. They designed chips that operate at extremely low voltages, reducing power consumption by over 1,000 times compared to conventional hardware. How much power are we talking about? The chip integrates tiny solar cells that generate about 75 nanowatts. To give you a scientific comparison, that is 100,000 times less power than what your smartwatch consumes. 75 nanowatts is basically the energy equivalent of a fruit fly thinking about a banana. And yet, for these robots, it's enough to run their entire cognitive existence. But a brain is useless if you can't move. And since you can't put a combustion engine or even a traditional electric motor on something this small, without the laws of physics laughing in your face, they went with an electrokinetic mechanism. This is where it gets really cool in sci-fi. They use applied electric fields to generate forces on the surrounding fluid. This allows the robot to swim through liquids without any moving mechanical parts. No legs to break, no propellers to get gunked up with microscopic debris. It's just pure, elegant physics. This choice makes the robots incredibly robust. The researchers even demonstrated that you can move these things around using micropipettes, transferring them from one sample to another like you're moving goldfish, and they just keep on ticking. No wear, no tear, just tiny invisible swimming. Now, how do you tell a grain of salt what to do? You can't use Wi-Fi. A Wi-Fi antenna for a robot this size would be like trying to put a satellite dish on a mosquito. Instead, they use light. Remember those solar cells I mentioned? They aren't just for power. They're the communication port. The same light pulses that provide energy are used to beam instructions directly into the robot's memory. And it gets better. Each robot has its own unique address. This means you can talk to specific robots in a group. You could have 1,000 of these things in a petri dish and tell robot number 422 to go left while telling robot number 891 to go right. This opens the door for swarms. We're talking about coordinated groups of robots that act like a school of fish. They can execute complex movements, follow specific paths, and react to their environment in real time. In one of their demonstrations, they showed these robots measuring the local temperature and reacting to it. They could actually navigate along a thermal gradient. If it's too hot, they move. If it's too cold, they pivot. They are essentially programmable living organisms made of silicon and light. And they can keep doing this for months as long as there's a light source nearby. A simple LED is enough to keep them alive and working. It's basically the most low-maintenance pet you could ever own, provided you don't lose it in a carpet. So why should we care? Aside from the fact that it's objectively awesome to have an army of penny robots, the applications in medicine and manufacturing are quite frankly revolutionary. Because these robots operate at the same scale as biological cells, they are the perfect candidates for inner space-style medical interventions. Imagine a future where instead of a massive dose of chemotherapy that nukes your entire body, you swallow a cocktail of a few million of these microrobots. They can navigate through your tissues, identify specific cancer cells, and deliver a microdose of drugs directly to the target. Or they can monitor the health of individual cells in real time. We're talking about a level of precision medicine that makes our current tech look like performing surgery with a sledgehammer. But it's not just about medicine. In the world of manufacturing, these robots could act as a microscopic labor force. You could have lots of these devices assembling microscopic components or building structures at a scale that traditional robotic arms can't even perceive. It's the ultimate bottom-up approach to construction. Instead of building a big machine to make small things, you just program small things to build even smaller things. This research, which has been published in heavy hitters like Science Robotics and the Proceedings of the National Academy of Sciences, PNAS, marks a definitive shift in the field. For years, we've been trying to break the millimeter barrier with robots that are actually autonomous. Plenty of people have made tiny things that move when you hit them with a magnet or a laser, but those are just puppets. These new guys? They have an internal logic. They are smart. According to the team, this is just the reference platform. Now that they've proven they can fit a computer, a power source, sensors, and an engine into a 300 micrometer box, the sky's the limit. Or rather, the floor is the limit because they're already at the bottom. Future versions could include new sensors for chemical detection, or even communication capabilities between the robots themselves, allowing them to talk to each other without needing a human to pulse a light at them. Think about the implications of that for a second. Autonomous, self-communicating swarms of microscopic robots that are cheaper than a piece of gum. It's either the greatest medical breakthrough in human history or the beginning of a Grey Goose scenario where a rogue swarm accidentally turns the moon into a giant pile of microchips. Knowing our luck, it'll be a bit of both. But in all seriousness, the engineering here is staggering. The fact that they've managed to bypass the need for mechanical parts by using electrokinetics is a stroke of genius. It solves the biggest problem of micro-robotics, friction. When you're that small, water feels like honey and friction is a nightmare. By moving the fluid itself, they've turned a weakness into a strength. And let's circle back to that 75 nanowatt power consumption. That is perhaps the most impressive part of the whole paper. We are living in an era where we struggle to make an electric car go 300 miles. Yet these guys have built a functional computer that runs on the energy equivalent of a ghost's sneeze. It's a testament to what happens when you stop trying to make things bigger and faster and start focusing on smaller and smarter. So what's next? The researchers are looking into integrating even more sensors. They want these robots to be able to detect specific biomarkers or pollutants. Imagine dumping a handful of these into a water supply and having them autonomously find and neutralize contaminants, then signal their location so they can be filtered out. Or imagine them living inside industrial machinery, constantly patrolling for microscopic cracks or wear and tear, fixing problems before they even become visible to the human eye. The era of the macro robot might be coming to an end, or at least, it's about to get some very small roommates. We spent decades dreaming of giant mechs and humanoid assistants, but it turns out the real revolution might be happening in a petri dish under a microscope. So next time you're at the dinner table and you spill a little bit of salt, take a good, long look at it. Because in a few years, that grain of salt might just be a highly sophisticated, autonomous robot programmed to check your cholesterol or assemble your next smartphone. And if it starts swimming toward your soup, Well, you've probably just witnessed the future. That's all for today's deep dive into the tiny. If you enjoyed this look at the microscopic future, do the YouTube thing, like, subscribe, and hit that bell so you don't miss the next time we talk about something that's probably already crawling on your skin. Stay curious, stay skeptical, and maybe buy a magnifying glass. You're going to need it. See you in the next one.